Yeah, anyways, let me continue. So we were talking about flips. And so there was a few pictures. For example, this is a flip, and then this is a flip, and this is a flip, and also we had some 3D examples. Where, this is a flip. And there is one more three-dimensional one where you can take a tetrahedron with a point inside. And you can either take the whole tetrahedron, or you can take the same tetrahedron, but you can make it 4 tetrahedra inside of one big tetrahedron. So these are all examples of what is called flips or bistellar flips. And yeah, so the question is, what is the structure? You give me an arbitrary configuration of points in R to the d minus 1, a point configuration in R to the d minus 1, and then I want to study these different triangulations with respect to these flips. So, for example, here are a few questions. So, first of all, by the way, what happens in general? So, I mean, this is unrelated to the flip story, but in general, here we have, if you look at how many polytopes I can get by taking the convex hull of D plus, right, so in each case, here is R to the D minus 1, and then I take the size of A is D plus 1, and these points form a circuit. And then I take the convex hull. So the question is, how many different polytopes do I get? So for example, here, question, how many generic, which for polytopes means simplicial polytopes in R to the D minus 1 with D plus 1 vertices. So this is D equals to 2. This is D equals to 3. D equals to 4. So the table should be for D equals to 2, I only get one polytope. For D equals to 3, I only get, well, this does not have D plus 2 vertices. D plus 1 vertices. Only this guy has D plus 1. So I have only one. And then for D equals to 4, in that example, I'll also, wait, am I? Say it again. Yeah, so that's the question. First of all, actually, for D equals to 2, I need a polytope with D plus 1 vertices. So this line segment is not a polytope with D plus 1 vertices. When D is 3, D plus 1 is 4, right? So I'm looking for a square in the plane. No, but the triangle has 3 vertices. Oh. Yeah, so I want to, yeah, so that's sort of a curiosity, like what happens in general, if I want to think of flips in arbitrary dimensions, then maybe I want to first see what happens if all points are in convex position and generic. So how many different pictures am I going to get? And so actually for d equals to 2, there is always, if you take 3 points on the line, one is going to be inside the convex hull of the other two. So actually here the answer is 0. Yeah, up to how many combinatorial types of simplicial polytopes in this dimension with this many words? That's the question. And actually the answer here is 0, and for d equals to 4, that's the only polytope. The answer is 1. And actually what happens in general is that for d equals to 5, the answer is going to be 2, and etc. So the answer is d minus 1, floor of d minus 1 over 2 is how many different combinatorial types you get. And this sort of I'm not going to explain why this is true, but if you are curious why this is true, then an easy way to see why this is true is to use Gale diagrams. Google Gale diagram. So the point is that even if the points are in convex position, once the dimension is high enough, you're going to get many different possible pictures of flips in those d plus 1 or d minus 1. Yeah. So anyways, this is all unrelated, so let me actually raise this. This is all very nice, but now let me ask some natural questions. Natural questions which are sort of a direct generalization from the association. So question number 1 is, are any two triangulations of A connected by a sequence of flips? And here, yeah, so let me assume that, let's say, assume that A is maybe in convex position and generic. Although, yeah, this is not really important, but let's assume that this is true. So you give me any two triangulations of some set of points. Is there always a sequence of flips which connects them together? And actually, yeah, we're going to vote on these. So there's going to be 3 questions. Second is, does each triangulation of A admit at least some number of flips? Some number of flips. So, and let's actually try to guess this number. So, what do you think the sort of natural guess for the minimal number of flips in terms of n and d? Yeah. Yeah, A has n points. A is inside R to the d minus. Say again? Yeah. Or even, let's say, n. I mean, n could be equal to d, in which case there is no flips. N minus d. Okay. What were we going to say? Oh. Right, you want to count triangulations. Okay. Wait, Kelly. Now, hold on. Flips. I want to fix one triangulation, and then I want to see how many flips does that triangulation have. Right. it's a different question, which is how many overall, what's the overall number of triangulations? Okay, n minus d is indeed a natural guess. Right, so here, d equals, well, when n is equal to d plus 1, you get that each triangulation has basically there's two triangulations, and each of them has exactly one available flip. So n minus d is one flip available. And when n equals to d, and n minus d is 0, so you get 0 flips available when your points form a simplex. And if for a polygon, d equals to 2, then you sort of get n minus 2 flips corresponding to the diagonals, where n is the number of vertices of your polygon, right? Yeah. Sorry, this is d equals to 3. Right, so d equals to 3, so your polygon lives in R to the d minus 1. All right, so okay, that's actually the correct, I'm trying to convince you that this is the correct natural guess. And the third question is sort of generalizing these two. So is there a polytope, some polytope Q, such that sort of I want to capture these triangulations into vertices of my, well, this should be like the association, right? So vertices of Q correspond to triangulations of A, and then the edges of Q correspond to flips, and etc. Well, and maybe the dimension of Q, maybe I want each vertex to have exactly the degree at least n minus d. So maybe the dimension is n minus d. Yeah, maybe, I mean, these are questions, right? So maybe, is it true for, maybe we should assume convex, or maybe not. So, all right, so now let's see what people think. What do you think? Yeah, let's actually. Say it again. Oh, you think? All right, so let me write it more precisely. A is in convex position, by which I mean that the convex tile of A has the set of vertices equal to A. So, but okay, you may or may not assume like whether in your answers to these questions. So the answer is not going to depend on whether it's convex or not. So what is the answer? What are the answers? Who thinks that the answer to the first one is yes? 1, 2, 3, 4, 5, 5. Okay. Who thinks that the answer to the second question is yes? 1, 2, 3. 3, yeah. Who thinks that the answer to the third question is true? 1, 2. Okay, 2. Right. Yeah, and I'm assuming the rest of the people think that the answer is no, right? Or if there's any sort of, yeah, okay. So actually, turns out that the answer to all questions is just no. So, but you are on the right track. So the answer is no. Right? So say again. They differ in. What do you mean differ in some amount of points? Okay. No, but what about, let's say I have a line segment. Let's say A is loss of points. And I have one triangulation like this, and I have another triangulation just includes all of these points. But these are connected by flips, right? Yeah, by sequence. Yeah, okay, by sequence of flips. Yeah, so it actually, I mean, yeah, so you have to speak louder because there is a window open, which, yeah. Yeah. So you're saying these are still not connected, or are you saying these are connected? Oh, wait. Yeah, because so you can, a flip allows you to take 2 points and then add a point in between, or remove a point in between. So you can add this point, this point. You can, it's actually, I mean, this here used to be a big open problem for many years. And then, yeah, so maybe I should mention, yeah, the counterexample to the first two questions. Actually, yeah, it's sort of remarkable. You can try to construct a triangulation which has this is called a flip deficiency. It has too few flips, and that's actually pretty tricky. And by pretty tricky, I mean that you would be very famous if you were the first one to find such examples. Anyway, so the famous person here is Santos. Santos in the year 2000. So he constructed a what did he do? He constructed a triangulation of 324 points in R to the 6 with 0 available flips. Yeah, how is it possible? Well, the answer is that your 3D intuition doesn't work in 6 dimensions. And yeah, so there's basically somehow there's such a rigid triangulation that you can't apply any flips. And yeah, actually, so that configuration here is not in convex position. But first of all, why does it? It actually answers all 3 questions in the negative. Yes, because yeah, for the first one, I mean, if you have an isolated point, then this graph is not connected. Second one, clearly the answer is no. And yeah, the third one, you can't have a polytope with an isolated vertex. So yeah, anyways, this gives you a counterexample. And if you want convex, there is a 234 dimensional polytope with 552 vertices, and which also has a triangulation that's isolated. Yeah. So you're asking, these questions are asking whether we can have a very natural analog of this association. Yeah. Yeah, the association answers all 3 questions in the affirmative. But in general, right, so you have these annoying counterexamples. Yeah, you're wondering if what's the lowest, and there's been big open problems about things in like low dimensions, 4 or 3, and I don't remember, but usually there's almost always a counterexample. For R3, I don't remember. R4, I think at least R4, there should be counterexample, and I think in R3 as well. Is there also 0 flips for? Yeah, 0 at a triangulation with 0 flips. So all these, there's, since the work of Santos, there has been many counterexamples, and they all look like this. There's always, you find an isolated triangle. People don't usually find all connected components of this graph. But yeah, and so this is very unfortunate, but let me tell you the good news. But the answers are yes, yes, and yes. If we restrict only to regular triangulations. Right. So remember, for polygons, all triangulations are regular. So what the associahedron actually captures is the structure of the regular triangle, and that works for arbitrary point configurations. So that's a construction which is pretty cool, and I'm gonna try to explain right now. Any questions so far? Yeah. Well, I mean, you mean the flips or the polytopes? For question 1, right? So yeah, if you wanna, for question 1, the answer is actually easy for regular triangulations, because how do you get a regular triangulation? You lift every point, and then you take the lower convex hull and you project down. Now, for each point, you choose a height to which you lift your point. Now, if you vary these heights generically, then it's easy to show that what's going to happen is that you're only going to apply a sequence of flips. If they change generically, then all that happens to your triangulations are just a bunch of flips. Yeah, in that sense, the answer one is pretty easy. Yeah, it's explicit, and I'm actually, yeah, it's due to the third part here is due to G.K. Gelfand-Kapranov-Zeleminski 94. So that's, I already told you about it, a realization of the associahedron using areas. So what I'm going to explain now is the generalization of that to arbitrary point configurations. If you think about it, it's actually pretty powerful, right? So any set of points, somehow you get a polytope for any collection of points. Right, so that construction is called secondary polytopes. And so again, I'm going to assume A side R to the D minus 1. And then the only thing I'm going to assume is that the affine hull of A is equal to R to the D minus 1. I'm not going to assume that they are in general position or anything like that. And maybe let me label them. So A1, A2, all the way up to AN. These are endpoints. And so here's a definition. GKZ94 is that suppose you have a triangulation of A. I'm going to introduce a vector that P sub T in, this is going to be very similar to what we did for polygons. Let v sub t be given by what I'm going to do is you can even guess what's going to happen. So triangulation is a bunch of simplices. Yeah, what should go here? Somebody can guess. Right. Yeah, except for triangles, you have simplices, but yeah, that's I say just sum up the volumes. So the sum of volume of sigma, where sigma is a simplex in subdimensional simplex in my triangulation, and AI. The only condition is that AI, right, the ith point has to be a vertex of sigma. All right, and then so the secondary. And here I'm actually going to do something slightly weird. So the secondary polytope, which is denoted of A, is denoted by sigma sub A, is just by definition you take the convex hull of all such vectors. So the weird thing here is that I'm taking T to be all possible triangulations. Triangulations of A. It doesn't matter if it's regular or not. I'm just taking all triangulations, and I'm looking at the corresponding set of points in R to the n. And so and it's a nice exercise to sort of to maybe take d to be 1, or well, let's say d to be 2. So if you look at one-dimensional point configurations, you get the secondary polytope is going to be some high-dimensional polytope. So it's nice to play with these examples and draw some secondary polytopes. Maybe yeah, you take like 4 points, 1, 2, 3, 4 on a line, and then maybe take these to be A, B, and C. And then C, just write down the coordinates of the polytope. It's going to be, yeah, or maybe, well, this corresponds to, this is some sort of a one-dimensional version of the associated heteron. These are like interesting polytopes. But anyway, let me state a theorem. Theorem PKZ94 is that, so there's 3 parts. First of all, the dimension of this, so this is clearly a polytope. Convex hull of a bunch of points. What is the dimension? Dimension of the secondary polytope is n minus d. And second claim is that the vertices of the secondary polytope, these are not all of these vectors, but only the ones corresponding to regular triangulation. V sub t, t is a regular triangulation of A. And the third claim is that the edges of sigma A, well, here let me assume that A is generic, and the edges of A are in bijection. They correspond to flips of regular triangulations. So that's the claim. And I'm not going to tell you the proof, but first of all, let me mention sort of one natural proof idea, which one of the first proof ideas for this statement is the following. Remark is that if you choose a vector h, capital H, inside R to the n, let's assume that it's generic. So if I choose such a vector, my polytopes, my secondary polytope lives inside R to the n. There's the inside R to the n. So if I take a generic function on R to the n, I can find the vertex. F sub h sigma a is going to be one of the vertices of your polytope. So one of the, by this claim, it's one of the regular triangulation. So which one? The question is, which regular triangulation do you get this way? Nice, right? So if you look at h, so h is an element of R to the n. So for each of its coordinates assigns a certain height to the corresponding point of a. So that's sort of exactly well, except you have to maybe replace h with minus h, because the response to the regular triangulation of the form I denoted it C sub h. You take lower faces of whatever of lifting each point ai, convex hull of lifting each point ai to h of ai. So, and because it's lower faces, you have to insert a minus sign, I think. But yeah, in general, so that's sort of the nice correspondence. As you vary h in general, right? So if it's generic, it gives you a vertex. As you change it in a generic way, your vertices are going to change, but they're going to be connected by edges. Very nice sort of natural structure. And but now let me address one of the homework problems. In your homework, for the icosahedron, you were supposed to prove one bound on the dimension. So you were supposed to find, in general, like there was 2 extra equations for the icosahedron. And in general, there is going to be, yeah, let's actually see what happens. So I want to prove so question that I want to address is that why is the dimension so such a small number? And so again, well, first of all, right, so it lives in R to the n, right? And so there's one obvious equation. One obvious equation is that if you take the sum of all coordinates, there is, for the icosahedron, if you take the sum of all coordinates, then by double counting sum of coordinates is equal to what, actually? So what is it going to be for arbitrary point configuration? Volume of which polytope? Volume of the convex hull. Nice. Volume of the convex hull of all points, and then somebody was times d. Okay, interesting. Times d, or should it be d minus 1? D, yeah, something like this. Yeah, times d, actually. Because each simplex is going to have exactly d points. Good. All right. So, but now, all right, for the other, we should still find d-1 equations. And remember, A lives inside R to the d-1. So we need to find this many independent equations. Yeah? Right. Yeah. So, right. And Jacob's solution for the tetrahedron actually generalizes to arbitrary configurations of points. So yeah, let me just write down what happens. So yeah, this, maybe I should write it like this, the sum over A. So I'm going to label the coordinates. There's n coordinates, and they correspond to points. So to avoid confusion, I'm going to do this like this. Sum of corresponding coordinates is d times the volume, the convex hull of, yeah, maybe let me call it q. Q, where q is the convex hull of A. Then what I want to do is indeed sum for each j from 1 up to d-1, there's an extra equation of the form sum over A inside over all points inside my point configuration of A, well, the jth coordinate of A times h of A is equal to, should be constant. And the constant is actually given by d times the integral, the convex hull of A of xj dx. So you integrate the jth coordinate over your convex hull, and then that quantity is going to be constant. It's going to be given by this sort of formula. And the reason is that if you have any linear or affine function on r to the d minus 1, maybe linear, then the integral of g of x dx over your polytope or over a simplex, or a simplex sigma simplex. So if you want to integrate a linear function over a simplex, then you can just, the answer is going to be given by sort of averaging the values at the vertices of your simplex. That's the general fact about integrals. 1 over d times the sum over all vertices of sigma of g of x, and then you have to multiply by the volume of sigma. So that's the formula for the integral. And because of that, you can count. So these basically you can, instead of here, you can put any linear function, and then you're going to have an integral of that linear function here. So all right, yeah, and somehow, yeah. So it's sort of not too hard to show that non-regular triangulations don't give you vertices. But there are actually there's some related open problems. There's some related polytopes, which are sort of more recent, and there are some open problems where it's this part here is it's an open problem. For some sort of analogs of secondary polytopes, yeah, second part somehow becomes an open problem. All right, any questions so far? All right. So no questions? All right, so what I'm going to do now is I'm going to start to slightly slowly transition into matroidal territory. And I'm still going to be talking about polytopes, but then it's going to slowly become, yeah, already here I'm considering arbitrary point configurations. And now the next thing I'm going to do is I'm going to consider Zonotopes, which again, going to be looking like I'm talking about polytopes. by definition, what is a zonotope? As it's something you have already all seen. A zonotope is by definition a Minkowski sum of line segments. Just take a bunch of line segments, so yeah, and then that polytope, you take the Minkowski sum, that polytope is called a zonotope. So, examples of zonotopes. Anybody? Yeah? The permutahedron, nice. So that's example number 2. Permutahedron, which, as you remember, 1/2 the sum over all positive roots of type a n - 1 of the line segment from negative alpha to alpha. And the picture is excellent. Cubes, nice. That's example number 1. 0, 1 to the n is, you just take the sum of all line segments from 0 to a basis vector. Also has a picture. All right. And actually, so let me give you one more example, which sort of is generalizing the second one, I think, and maybe also the first one. So another example is what is called a graphical zonotope. And so what is this thing? Let's say G is a graph, just an undirected graph. And let's maybe the set of vertices of G is, let's just label the vertices by bracket n. The vertices are labeled by 1 through n. How do I define a zonotope for a graph? What would be a natural guess? Oh, so you want a two-dimensional example? Yeah, okay, that's not the one I intended. Okay, so you want to put your graph in a circle. Oh, nice. EI, EJ. Okay, nice. Yeah, that's the intended guess. Okay, so sum over all I and j which form an edge, and then I just take the line segment from EI to EJ. Interesting. Well, I mean, this is also interesting, but yeah, I've never seen this construction here. But yeah, this construction is sort of what you naturally get. And by the way, right, so in what sense does this example generalize the permutahedron? All right, so we want to take a graph whose vertices are positive roots. Whose vertices are all the roots, and then okay, but then so okay, so we want to take a graph to be a bunch of disconnected edges like this. And let's actually see what happens. So if you take a bunch of disconnected edges, then you can label the vertices Say again? Hmm? Yeah, I'm sorry. I can hear like every second word of the. But then you have to specify a graph, right? With that graph. Okay, so let's say my graph is a bunch of disconnected edges. Right, then the corresponding, so if I label 1, 2, 3, 4, right, but these are not quite the roots, right? These are, oh, so you still wanna take vertices to the, okay, so the vertices correspond to systems of positive roots, and they're connected whenever there's a reflection connecting one to the other. Yeah, that's actually, the answer is actually, well, maybe I should, hmm? Well, actually, n choose 2, right? So yeah, let's, I mean, this is true for arbitrary root systems, but let's take type A. Say I'm only working with type A. Then, yeah, the actual answer is actually much easier. So let me, do I tell you, or do you want to guess for the remaining 2 minutes? Do edges correspond to reflections? Actually, well, the edges should correspond to positive roots. Yeah, this formula should be almost the same as this formula. Oh, nice. It's just Kn. Okay, so, and actually that's correct. So up to shift, the graphical zonotope for the complete graph, Kn, is just equal, or maybe it's equal up to shift to the permutahedron of type A n minus. Yeah. Something like this. Wait, hold on. No. Right, the Newton polytope was asking, well, I mean, we learned this fact, the second fact we learned a while ago, right? And the homework was asking to reprove this fact using the van der Monde identity. Yeah, but then, right, so that's actually a good question. I don't think there is a generalization for arbitrary root systems. So, because usually, yeah, what happens for type AN, you can talk about these sort of, there's these roots and there's also the actual basis factors, right? Like E1, E2, etc. And for arbitrary root systems, there is not a natural notion of these basis factors. You can still talk about roots and fundamental weights and whatever, but the actual, like, yeah, I don't know what's the analog of Kn for arbitrary root systems. Okay, I'm almost out of time. But yeah, but maybe I should explain. So up to shift, if you shift your zonotope properly, then each line segment here becomes just this line segment. Instead of, if you shift by ei plus ej over 2, then this becomes negative alpha to alpha. And yeah, I should just stop. But I'm going to see you all on Wednesday, everybody.